There are moments in the quiet of night when a simple question can open a doorway to the entire universe. Why do objects fall in exactly the way they do, following invisible curves that no one can see but everyone can feel? Why does the ground rise to meet us with perfect certainty every time we step forward? And what truly shapes the paths of planets that glide through the darkness with impossible precision? If gravity is everywhere, why is it so difficult to isolate, measure, and understand? And perhaps the most unsettling question of all is this: if gravity is the oldest force we have ever studied, why did we spend so many centuries misunderstanding it, limited by the very world that held us down? These questions are not riddles. They are real scientific puzzles that once stood like locked doors before some of the greatest thinkers who ever lived. Their answers would eventually reshape our view of reality itself, but only once humanity learned to look beyond the surface of the world and into the profound structure beneath it. To understand gravity with honesty and scientific clarity, we have to begin long before rockets and satellites and the great observatories that now orbit high above the atmosphere. We must return to a time when the only laboratory available to a scientist was the Earth beneath their feet. Every experiment was limited by the turbulence of air, the shaking of the ground, and the inescapable truth that nothing on Earth can stay in free fall for more than a fleeting instant. Even so, that was the world in which Isaac Newton first realized that the same force that made an apple drop gently toward the soil also guided the planets in their slow and stately arcs around the sun. His idea was monumental. Gravity was no longer a simple downward pull, but a universal attraction acting between every pair of masses in existence. Yet his understanding, brilliant as it was, depended entirely on the ways that gravity behaved here on Earth, where friction and air resistance and the solid ground distorted nearly every measurement. Newton saw farther than any of his time, but even his vision was bound by the limits of the planet on which he stood. For centuries, scientists clung to Newton's law of universal gravitation because it worked remarkably well for nearly everything the world could test. It predicted the motion of the moon, the tides, the path of comets, and the delicate orbits of the planets. But there were hints that Newton's framework was incomplete, subtle deviations that demanded deeper explanations. The orbit of Mercury shifted in a way that Newton's equations could not fully capture. The speed of light behaved as though it carried more significance than a mere number describing illumination. And the very notion of space and time seemed to resist the idea that they were fixed and absolute. These were small clues, but they signaled a profound truth. Gravity might not be a simple force acting across empty space. It could be something woven into the geometry of space and time itself. When Albert Einstein arrived with the theory of general relativity, the scientific world found itself standing before an entirely new landscape. Space and time were no longer separate backgrounds, but a single fabric that could bend and stretch. Mass was not pulled by a force, but compelled to follow the curved shapes of space-time. Gravity became geometry. This idea changed everything, and yet even this revolutionary understanding was still grounded entirely in Earth-based measurements, telescopic observations, and clever laboratory experiments. Einstein's equations predicted phenomena like the bending of starlight near the sun and the slow precession of planetary orbits. But the world had only a limited capacity to test these predictions. Instruments were confined to the surface. Free-fall experiments lasted only the brief duration of a dropped object, and the constant shaking of the planet made it difficult to isolate the faint whisper of gravitons or the delicate distortions expected from massive bodies moving through space-time. Earth, for all its beauty, is a noisy and restrictive place for studying gravity. Seismic vibrations ripple through the crust at all hours. Atmospheric turbulence nudges telescopes out of alignment. Air drag alters the motion of falling objects. Even the most carefully controlled laboratory could never provide more than a moment of true free fall. Scientists used drop towers that offered a few seconds of zero weight conditions, but these were nowhere near sufficient to explore the deeper structure of gravity. The planet itself was the problem. It kept every object pinned down, leaving researchers with only a narrow window into a force that operates across the universe with seamless precision. For gravity to be understood in full, researchers would need a laboratory without walls, without trembling floors, without the omnipresent drag of air. They needed a place where an object could fall forever without hitting the ground. This limitation is the reason why the space age became not merely an era of exploration, but a scientific necessity. The moment the first satellites were launched into orbit, humanity gained something it had never possessed before: a stable, long-duration free-fall environment. An orbiting spacecraft is not floating. It is constantly falling toward Earth, but moving forward fast enough that it keeps missing the ground. This continuous free fall is what scientists call microgravity, and it cannot be replicated naturally anywhere on Earth. Microgravity transformed space into a perfect gravitational laboratory, a place where motion could be observed without interference, where Einsteinian predictions could be tested at scale, and where gravity's subtleties could finally be measured with unprecedented clarity. The early space missions marked the beginning of this shift. Sputnik and Explorer were not only symbols of a global contest, but also the first objects that allowed direct testing of gravitational laws beyond the planet's surface. Their trajectories revealed slight deviations from predicted paths, not because the theories were incorrect, but because the space environment exposed new layers of gravitational complexity that Earth-based experiments had never been able to resolve. By tracking these satellites with increasing precision, scientists confirmed aspects of Newton's and Einstein's frameworks and uncovered new questions that would guide space-based research for decades to come. Humanity had stepped into a realm where gravity could finally be studied truthfully. Far from the noise of the planet and free from the constraints of Earth-bound experiments, space offered a vantage point that no scientist from Newton to Einstein could have imagined. The journey of understanding gravity had begun long before the first rocket ignited, but its most profound insights would emerge only once humanity left the ground behind. The moment humanity placed its first instruments beyond the atmosphere, gravity revealed that it was far more dynamic than Earth-based experiments had ever allowed us to see. On the ground, every falling object is swallowed immediately by friction and collisions, its path distorted by air, resistance, and the hard surface that ends every descent. But in orbit, motion unfolds on a scale that is both pure and uninterrupted. A satellite released from a spacecraft traces a path that is not guided by engines or pushed by winds. It drifts along a curve defined only by gravity and inertia, following the geometry of spacetime itself. This is what made the earliest orbital measurements so transformative. They showed us gravity not as a force struggling through the noise of a laboratory, but as a clean and elegant phenomenon shaping motion with astonishing precision. Scientists quickly realized that the new vantage point of orbit could refine gravitational measurements beyond anything achieved in centuries. When engineers monitored the paths of the first satellites, they discovered that even tiny variations in Earth's gravitational field could influence their motion in measurable ways. Slight differences in the planet's mass distribution, such as mountain ranges, ocean trenches, and mantle convection patterns, left subtle signatures on orbital trajectories. No Earth-based experiment had ever revealed these details, because the noise of daily life on the surface drowned out their signals. In space, however, satellites felt every nuance of gravitational variation. This opened a new frontier in geophysics, where the study of gravity became a method for understanding the internal structure and behavior of our planet. Yet despite these advances, there remained a deeper challenge lurking beneath the surface. For all of the success Newton's laws had delivered, and for all the elegance Einstein had added to the picture, the real test of gravity required more than observing Earth from above. It required pushing into distances where planetary influences blended with the gravitational pull of the Sun, where the effects of curved spacetime could stretch over millions of kilometers, and where spacecraft moved with velocities and trajectories that no Earthbound test could ever reproduce. The problem was not that scientists lacked equations, but that they lacked data from these extreme regimes. Gravity behaves differently when objects move at high speeds, when light passes near massive bodies, and when the geometry of spacetime warps across vast regions. These were not theoretical curiosities. They were experimentally measurable effects, but only if humanity could send instruments far beyond the cradle of Earth. The early interplanetary missions began to chip away at these questions. As probes traveled through the solar system, their radio signals provided exquisite measurements of their positions and velocities. The timing of these signals was sensitive to both classical gravitational effects and relativistic ones. For example, when signals from a spacecraft passed near the Sun, they took slightly longer to arrive on Earth because the curvature of spacetime increased the distance light had to traverse. This phenomenon, known as the Shapiro time delay, was predicted by general relativity and confirmed through these missions with remarkable accuracy. Earth-based laboratories could not reproduce such conditions because they lacked both the necessary distances and the ability to send signals skimming close to massive bodies. Space filled this gap perfectly, giving humanity a way to test Einstein's predictions directly through real data, instead of relying solely on indirect measurements or astronomical observations. Another profound insight came from observing the precession of planetary orbits with far greater precision. Mercury had long been known to deviate slightly from Newtonian predictions, a deviation fully explained by general relativity. But the true power of this effect could only be explored through spacecraft tracking. As missions traveled closer to the Sun or swung through gravitational assists around planets, their paths were influenced by the curvature of space-time. These path deviations were tiny, but the radio instruments used to track them had sensitivities measured in fractions of nanoseconds. Every slight bending of the signal or shift in trajectory became a data point for testing and refining our understanding of gravity. These were not hypothetical effects, but real measurable phenomena that unfolded in the vacuum between worlds. The interplanetary probes also revealed something deeper about the relationship between gravity and motion. On Earth, we often imagine gravity as a downward pull, a force with direction and clarity. But in space, gravity becomes a dance between mass and geometry. A spacecraft coasting through the solar system does not feel gravity as a tug in one direction. Instead, it follows a path carved out by the curvature of spacetime created by the Sun and the planets. This path is not fixed. It shifts depending on velocity, distance, and the mass of nearby bodies. Observing how a probe moves through these regions allowed scientists to measure the geometry directly. The data showed that Einstein's description of gravity as spacetime curvature remained consistent even under conditions far more extreme than those found on Earth. As missions grew more ambitious, a new and unexpected puzzle emerged. When scientists tracked the trajectories of the Pioneer probes, they noticed a slight persistent deceleration that did not match predictions. The effect was tiny, far smaller than any influence that could change the course of a spacecraft dramatically, but it was present and measurable. For a time, this anomaly sparked intense debate. Some wondered whether it hinted at new physics, while others suspected an unaccounted source of force. Decades of analysis eventually revealed the answer. The spacecraft emitted heat unevenly, and this thermal radiation produced a tiny recoil force that slowed the probe slightly. This discovery served as a powerful reminder of how meticulous scientific inquiry must be. Nature had not violated the laws of gravity. Humanity had simply needed to understand every component of its machines before interpreting the universe around them. The resolution of the Pioneer anomaly stands as a testament to the care required when exploring phenomena that operate at the faintest edges of detection. By the time these early missions concluded, gravity had already transformed from a simple downward pull into a rich and multi-layered phenomenon shaped by mass, motion, and the very architecture of space and time. The world now had undeniable evidence that Newton's equations were deeply useful but incomplete. that Einstein's vision of curved spacetime was correct across multiple scales, and that the true nature of gravity would only grow clearer as humanity ventured deeper into space. Each mission had revealed a piece of a larger picture, pointing to the same conclusion. Understanding gravity fully required not just better instruments, but a new environment, one that Earth could never provide on its own. The story of gravity had crossed oceans of time, from the falling apple of Newton to the bending starlight observed during solar eclipses. But with the dawn of space travel, this story entered an entirely new chapter, one defined by direct experimentation rather than distant observation. The sky was no longer a barrier. It had become a laboratory. And this laboratory, bound by no walls and shaped only by the geometry of the universe itself, would allow scientists to chase questions that once seemed far beyond reach. The most profound transformation in our understanding of gravity did not arrive through mathematics alone. It emerged through experience, through the quiet drift of satellites, the steady hum of radio transmitters, and the silent motion of spacecraft slipping through regions of space that no human eye had ever seen directly. In these distant places, gravity behaved with a clarity that Earth could never provide. The absence of air, the absence of shaking ground, and the absence of constant friction created a realm where motion followed its purest form. And this purity of motion allowed scientists to uncover layers of gravitational behavior that had been invisible for centuries. The early missions had shown us how gravity shaped the paths of spacecraft, but it was the precision tracking and timing systems that revealed how subtle, how delicate, and how intricate gravitational effects could be. Radio signals sent across millions of kilometers returned with timing differences so small that only advanced atomic clocks could detect them. These differences were not flaws or errors, but the fingerprints of space-time itself. Whenever a signal traveled near a massive body, its journey was stretched by the curvature of space. Whenever a spacecraft moved fast enough, time itself flowed differently for the instruments on board. These were not philosophical concepts. They were measurable realities, confirmed repeatedly by missions traveling through the solar system with astonishing accuracy. As gravitational understanding deepened, a new question emerged. If gravity could influence time and shape the paths of light, how much of the universe was controlled by phenomena we had not yet seen? Across the 20th century, astronomers noticed that galaxies rotated faster than expected, as though some unseen mass held them together. Instead of drifting apart, galactic stars remained bound by a gravitational pull stronger than the visible matter could account for. This invisible mass, later called dark matter, did not shine, reflect, or interact with light. It only revealed itself through gravity. The realization that most of the mass in the universe was invisible reshaped cosmology forever. Yet even this monumental discovery was grounded in evidence, not speculation. It was gravity that told the truth. It was gravity that traced the hidden structures of the cosmos. The arrival of space-based telescopes strengthened this evidence in ways Earth-based observatories could never match. Freed from atmospheric distortion, telescopes like Hubble captured the bending of light from distant galaxies with stunning clarity. This bending, known as gravitational lensing, confirmed the presence of massive structures that could not be seen directly. Space-based observations showed arcs of distorted light stretching across the sky, each one a map of the dark matter buried within clusters of galaxies. These measurements proved that gravity reacts not just to visible matter, but to everything possessing mass or energy. In this way, gravity became both a physical force and a cosmic detective, revealing what the universe is made of even when no other evidence remained. Yet the largest shock came when observations of distant supernovae revealed that the expansion of the universe was accelerating. Instead of slowing down under the pull of gravity, galaxies were speeding apart. This meant that some form of energy, later called dark energy, was pushing the universe outward. The idea sounded almost impossible at first. How could the cosmos accelerate without any visible cause? But again, this was not speculation. It was a direct result of careful measurements using space-based instruments that could detect small differences in brightness and distance too subtle for Earth-based telescopes. Gravity was not merely shaping the paths of planets and stars. It was responding to the deepest contents of the universe, including influences that could not be seen or touched. The force that once explained apples falling from trees had now become the key to understanding the fate of the cosmos itself. As these discoveries unfolded, scientists faced a powerful realization. Even though general relativity had explained a vast range of gravitational phenomena with remarkable accuracy, it still did not answer every question. The nature of dark matter remained unknown. The cause of dark energy was still a mystery, and at the smallest scales, where quantum mechanics ruled, gravity refused to fit neatly into the picture. These gaps were not failures. They were invitations, open doors that scientific exploration had not yet passed through. And the key to unlocking them lay in space, where gravity could be studied without interference, where quantum systems could behave freely, and where instruments could drift undisturbed for months or years at a time. The Earth, for all its strength and stability, could never offer such conditions. Laboratories on the surface were limited by constant vibrations, fleeting freefall durations, and the atmospheric turbulence that plagued every optical measurement. Even the most sophisticated experiments were confined by the planet itself. But space was different. It offered long-duration microgravity conditions, vast distances, extreme velocities, and the silence needed for sensitive measurements. In space, a drop of water floated as a perfect sphere. A flame burned in a shape the Earth had never seen, and atoms cooled to near absolute zero revealed quantum properties that had remained hidden in the noise of the surface. Space was not just another laboratory. It was the only environment where gravity could be observed in its most fundamental and unfiltered form. By the end of the early space age, scientists understood that gravity was not merely a force pulling downward, but a cosmic architecture underlying everything from planetary orbits to the expansion of the universe. The path from Newton to Einstein, from Earth-based observations to orbital experiments, had revealed that gravity is both familiar and deeply mysterious. It shapes the motion of falling objects and the evolution of galaxies. It guides the trajectories of spacecraft and the flow of time itself. And it continues to challenge humanity with questions that reach beyond the visible world. As the 20th century closed, one truth had become undeniable. To understand gravity fully, humanity would need to leave Earth behind. The universe was no longer just a backdrop for scientific inquiry. It had become the laboratory itself. And in that laboratory, gravity was waiting with secrets that no planet-bound experiment could ever reveal. There is a moment in orbit when everything becomes silent in a way that Earth could never imitate. A wrench floating beside an astronaut does not drift because of wind or vibration. It drifts because nothing is anchoring it anymore. Not the ground, not the air, not even the subtle resistances that shape every movement on the surface. It is a realm where motion unfolds according to gravity alone, unfiltered and undistorted. This strange environment, called microgravity, became the first true laboratory beyond Earth, a place where nature revealed behaviors that had always been hidden from view. The quiet drifting of an object in orbit is not the absence of gravity, but the pure experience of it, because an object in orbit is falling endlessly, tracing the curve of Earth with such precision that it never touches the ground. To understand why microgravity became such a powerful scientific tool, one must imagine everything that Earth imposes on an experiment. Even the most controlled laboratory is filled with minute vibrations from passing vehicles, from ocean tides, from shifting air currents, and from the constant rumble of life on the surface. A falling object on Earth is immediately slowed by drag, rapidly halted by the floor, and never allowed more than a handful of seconds in free fall. By contrast, an orbiting spacecraft provides continuous free fall for months or even years at a time. This uninterrupted descent creates an environment where forces as faint as those governing the behavior of thin films of liquid or the motion of ultra-cold atoms can finally be observed without interference. When the first astronauts entered orbit, they discovered that microgravity was more than a new environment. It was a new way of experiencing the laws of nature. Liquids no longer pooled at the bottom of containers, but formed perfect spheres. Flames no longer rose because warm air did not drift upward. Instead, fire formed calm, rounded halos of light, revealing the pure chemistry of combustion without the turbulence that Earth always forces upon it. Even the simplest action, like stirring a spoon in a cup, produced patterns that no Earth-based experiment could replicate. These changes were not curiosities. They were the foundations of a new approach to physics, chemistry, and biology, where the absence of weight allowed scientists to observe phenomena that had been invisible for centuries. The International Space Station became the centerpiece of this effort. Orbiting Earth in continuous free fall, it served as a platform for experiments that required long durations of microgravity. Its laboratories became places where crystals grew with extraordinary purity, where fluids arranged themselves into shapes dictated only by surface tension, and where materials science progressed in ways that no ground-based facility could match. Protein crystals grown aboard the station revealed structures with far greater clarity than those produced on Earth. This improved. Clarity allowed researchers to understand the atomic architecture of proteins with unprecedented detail, aiding the development of medical and research applications that depended on knowing exactly how molecules assemble themselves. One of the most transformative discoveries involved the behavior of fluids. On Earth, liquids are shaped by gravity and the surfaces that contain them. But in microgravity, surface tension and molecular interactions dominate. The result is a world where water can crawl through narrow passages, cling to edges, and form bridges between surfaces with behaviors that are both mesmerizing and scientifically invaluable. These insights helped engineers design systems for fuel storage, water recycling, and cooling aboard spacecraft. They also revealed how fluids behave in environments far from Earth, knowledge that is essential for planning long-term missions to the Moon, Mars, and beyond. Microgravity also created opportunities to observe physical processes in their simplest forms. For example, researchers studying combustion discovered that without gravity-driven convection, flames burned cooler and more uniformly. Instead of stretching upward, they curled into small, spherical shapes with faint blue edges. This surprising behavior allowed scientists to study how fire spreads, how fuel and oxygen mix, and how materials ignite in ways that Earth's gravity always hid. These discoveries were crucial for improving fire safety in spacecraft and for understanding the fundamental chemistry of flames. None of it would have been possible in the turbulent air currents of Earth. Perhaps the most profound experiments on the station involved the study of quantum systems. Atoms cooled to near absolute zero behave differently when freed from the constant pull of gravity. They spread out slowly, their wave-like properties becoming easier to measure. In this environment, scientists formed Bose-Einstein condensates, a state of matter predicted decades earlier but difficult to study on Earth because gravity made the atoms settle too quickly. Aboard the station, these delicate clouds of ultra-cold atoms drifted freely, unburdened by weight, giving researchers a chance to observe quantum phenomena with clarity that had never been achieved before. The station also allowed for long-duration atom interferometry, a technique where the wave-like nature of atoms is used to make extraordinarily precise measurements. On Earth, these experiments are limited by the brief time that atoms can remain in free fall. In orbit, however, atoms can drift for long periods without hitting the ground, allowing interferometers to detect subtle variations in gravitational acceleration, tiny movements of the spacecraft, and other faint influences that would be lost in the noise of Earth-based laboratories. These experiments became essential for improving navigation systems, studying general relativity, and preparing for future missions that would attempt even more. sensitive quantum measurements. In microgravity, even biological systems behaved in surprising ways. Cells moved differently, tissues grew in unfamiliar patterns, and the human body responded to the lack of weight by shifting its internal fluids and altering the balance of muscles and bones. These effects were not only medically significant, they revealed the deep connection between gravity and life itself. Every living organism on Earth had evolved under the constant pull of gravity, and the moment the pull was removed, biology shifted into a new mode. Studying these changes taught scientists how gravity influences cellular behavior and how the human body must adapt for long-term missions to distant worlds. As the decades passed, the International Space Station proved that microgravity was not a novelty, but a scientific necessity. It became the one environment where experiments in physics, chemistry, biology, and engineering could be performed without the distortions that had limited research for centuries. It provided data that transformed our understanding of fluid behavior, combustion, material science, and quantum phenomena. Most importantly, it demonstrated that the universe offered laboratories far more versatile and revealing than anything built on Earth. Microgravity allowed scientists to peel back layers of complexity and see nature as it truly is, unfiltered and unbounded. And so, orbit became the new frontier of gravitational exploration, a place where falling forever was no longer a poetic idea, but a practical reality. The insights gained from this environment did not replace the work of Newton or Einstein. Instead, they expanded it, revealing how the laws of gravity operate when Earth's limitations are removed. Microgravity became the bridge between Earth-based physics and the cosmic scale effects explored by interplanetary missions. It showed that gravity is not simply a downward pull, but a universal influence shaping motion in ways both subtle and profound. The laboratory of orbit had opened, and the journey into the deeper structure of gravity had only just begun. The deeper scientists ventured into the world of microgravity, the clearer it became that the absence of weight was not simply an unusual condition, but a profound shift in the balance of physical forces. On Earth, gravity dominates every movement, every drop of water, and every rising column of warm air. But in orbit, other forces that had always been overshadowed suddenly stepped into the foreground. Surface tension, molecular interactions, quantum behavior, and even the subtle influence of thermal radiation began to dictate the behavior of matter in ways that felt almost alien. What seemed at first to be an environment of stillness and calm was in truth a world where nature expressed itself with remarkable honesty, revealing processes that Earth had hidden under layers of gravitational influence. One of the first revelations came from observing how mixtures separated, combined, or remained suspended. On Earth, heavier components sink while lighter ones rise, creating convection currents that stir and rearrange materials constantly. In microgravity, these patterns disappeared entirely. A mixture that would have separated into layers on Earth remained perfectly blended in orbit. Components that would have drifted apart under the influence of gravity stayed suspended like tiny planets in their own miniature universe. This allowed researchers to study diffusion, the slow wandering of molecules through a fluid, without the interference of buoyancy or convection. Such clean conditions made it possible to test theories of molecular motion and chemical mixing with accuracy that had never been achieved on Earth. Even simple materials behaved in striking ways. Molten metals cooled into smooth, uniform shapes without sinking impurities because gravity no longer dragged heavier elements downward. This uniformity had significant implications for materials science, revealing how metals solidify and how their internal structure changes without gravitational effects. These experiments taught researchers how to design materials with fewer flaws, more resilient crystal structures, and improved performance. These insights would later become essential for building spacecraft components, able to withstand extreme temperature changes, radiation exposure, and the constant stress of orbital motion. the study of capillary action also entered a new era in microgravity. On Earth, liquids climb narrow tubes only a short distance before gravity pulls them back down. But in orbit, gravity does not pull them down at all. As a result, water and other fluids can travel extraordinary distances through narrow channels, guided solely by molecular attraction and the shape of the surfaces they touch. Understanding this behavior became essential for designing life support systems, fuel tanks, and cooling technologies aboard spacecraft. It also revealed how fluid motion depends on the delicate interplay between molecular forces and geometric constraints, a dance that had been masked by gravity for millennia. Another cornerstone of microgravity research involved studying how living organisms respond when the constant tug of gravity disappears. Plants sprouted in unusual directions, guided not by weight but by light and chemical signals. Their roots wandered through soil without a sense of up or down, revealing how deeply gravity shapes the biological choices of every organism on Earth. Bacteria grew differently as well, forming clusters and patterns that did not appear in ground-based experiments. Some species revealed new metabolic pathways, while others became more or less virulent. These changes were not signs of danger, but windows into the intimate relationship between life and the gravitational environment in which it evolved. The human body, too, responded in ways both subtle and profound. Without the constant downward pull, muscles adapted by shedding unnecessary mass, while bones lost density because they no longer carried weight. Bodily fluids, normally drawn downward, shifted toward the chest and head, altering circulation and even changing the shape of an astronaut's face. These effects were not merely curiosities. They revealed the extent to which gravity is woven into every biological system, guiding the structure of bones, the composition of blood, and the organization of cells. Studying these changes helped scientists understand how long missions to the Moon or Mars must be planned, and how the body can be protected during extended periods of microgravity. Perhaps the most delicate and intricate discoveries came from the behavior of quantum systems in orbit. The microgravity environment was ideal for studying ultra-cold atoms because the atoms were not forced downward by weight. When cooled to near absolute zero, atoms in orbit expanded slowly, allowing their wave-like nature to unfold with remarkable clarity. These drifting clouds of matter formed Bose-Einstein condensates that lived longer, remained more stable, and revealed more detail than any produced on Earth. Observing these quantum states gave researchers a way to test fundamental physics, including theories of coherence, superposition, and the relationship between quantum behavior and gravitational influence. This growth in quantum research led to the development of instruments that required space-based conditions to function at their full potential. Long-duration atom interferometers were able to measure acceleration and rotation with astonishing sensitivity, because the atoms inside them floated freely for long periods without touching container walls. These devices demonstrated the potential for spacecraft to become quantum observatories, capable of detecting tiny shifts in gravitational fields, mapping variations in Earth's mass distribution, and potentially exploring the interface between general relativity and quantum mechanics. Through all these experiments, one truth became increasingly clear. Microgravity was not simply a novelty created by space travel. It was a missing chapter of physics, a realm that Earth had never allowed scientists to access. The discoveries made aboard the International Space Station and other orbiting platforms revealed aspects of nature that had been invisible throughout all of human history. Gravity is such a dominant force on the surface of Earth that it quietly shapes every experiment, every observation, and every living process. Only by removing that influence could scientists see how matter behaves when left to its own devices. This realization transformed the role of microgravity in science. It was no longer seen as a condition to work around, but as a tool to explore the universe at its most fundamental level. Understanding how fluids flow, how atoms drift, how flames burn, and how life adapts without gravity provided insights that reached far beyond orbit. These discoveries laid the scientific foundation for future missions, for spacecraft design, for deep space navigation, and for the study of physics at both the largest and smallest scales. Microgravity, once thought of as an exotic side effect of orbit, became the first true laboratory beyond Earth. It revealed that gravity is not simply a force, but a context, a constant shaper of matter and motion. In its absence, a new clarity emerged. And through that clarity, scientists saw the universe with fresh eyes, realizing that the journey to understand gravity had only just begun. The more scientists worked within microgravity, the more they realized that they were confronting a profound truth about the universe. Gravity, which seemed so familiar on Earth, had been quietly controlling every detail of physical behavior in ways no one had fully understood until it was removed. The moment weight disappeared, familiar processes unraveled into new forms, revealing their pure underlying mechanisms. What had once been background noise became a central question. How deeply does gravity influence the behavior of matter? How much of what we take for granted about motion, heat, life, and structure depends on the constant downward pull that we rarely notice? Orbit provided the first honest answers. One of the most surprising insights came from the study of heat. On Earth, heat rises because warm air expands, becomes lighter, and lifts away from cooler air below it. But in orbit, no such rising occurs. Warm air does not drift upward, because upward has lost its meaning. Instead, heat spreads evenly in all directions, moving only through conduction or the gentle stirring of ventilation systems. This presented both a challenge and an opportunity. Fire behaved differently. Flames did not leap or stretch. They formed small, nearly spherical shapes, revealing the pure chemistry of combustion without the turbulence of convection. These soft, floating spheres of flame allowed scientists to study ignition, fuel mixing, and flame extinction with unprecedented precision. The results helped engineers improve spacecraft fire safety systems and offered new insights into how materials burn, insights that would have remained hidden on Earth where gravity constantly stirs the air. The removal of convection also shaped how biological systems behaved. Cells depend on fluid movement to transport nutrients and remove waste. Without gravity, these flows no longer occurred naturally. Instead, they slowed to a near stillness, forcing cells to rely purely on diffusion and molecular interactions. This change affected how tissues grew, how bacteria formed colonies, and how microorganisms responded to stress. On Earth, gravity quietly influences cell shape, division, and orientation. In orbit, these guiding forces vanished, revealing the deeper rules that govern life at the microscopic scale. Some cells grew faster, some slower, and some rearranged themselves into patterns that Earth-based. Biologists had never witnessed before. These discoveries were not anomalies. They were the natural expressions of biology, freed from a force that had shaped evolution for billions of years. As microgravity experiments multiplied, scientists began to understand the fundamental importance of surface tension. On Earth, surface tension is overshadowed by weight. It pulls the surface of water into smooth curves, but gravity quickly flattens those curves. In orbit, however, surface tension becomes dominant. Water clings to surfaces, crawls along edges, and forms bulging spheres that merge or split with delicate precision. These behaviors allowed researchers to observe how liquids organize themselves when gravity no longer compresses or stretches them. This understanding became essential for designing systems that use fluids in space, including fuel management, cooling loops, hydration supplies, and environmental systems. Engineers began to design spacecraft components not based on how liquids behave on Earth, but on how they behave in microgravity, where the rules of motion shift and new challenges appear. The microgravity environment also provided an unprecedented opportunity to refine measurements of physical constants. The behavior of pendulums, oscillations, atomic transitions, and wave propagation all change subtly when gravity is reduced. These changes created a new avenue for testing foundational theories in physics. When atoms float freely, their internal energy shifts become easier to measure. When suspended objects drift without friction, their motion becomes a clean canvas for observing the faintest forces. This purity of motion allowed researchers to evaluate predictions from general relativity and quantum mechanics with a level of precision Earth-based laboratories could not match. In many ways, microgravity became an amplifier of subtle truths. It magnified behaviors that were too faint to see under the weight of Earth. It made visible the quiet forces that shape matter at every scale. The International Space Station became more than a vessel orbiting the planet. It became a scientific lens, bringing into focus the intricate interactions that gravity normally conceals. Scientists used this lens to look deeper into fluid dynamics, into the structure of crystals, into the complexities of fire, and into the whispering motion of quantum particles. As researchers accumulated data from these experiments, they began to imagine what might be possible with even more refined microgravity platforms. Dedicated free-flying laboratories, unburdened by the vibrations or movements of a large station, could provide even purer environments. Ultra-cold atom facilities launched aboard sounding rockets revealed how quantum systems behave when given brief minutes of microgravity. Their results inspired the design of new modules and instruments destined for orbit, where they could operate for months or years. The potential to observe quantum behavior on large scales and over long durations opened doors to testing foundational concepts that sit at the boundary between general relativity and quantum theory, a frontier that has remained elusive for decades. The success of microgravity studies also changed the way scientists approached the idea of exploration. Space was no longer simply a destination, it had become a tool, a necessary extension of the laboratory. Without it, entire branches of science would remain incomplete. The idea that gravity shapes every phenomenon on Earth had been known for centuries, but only by leaving gravity behind could humanity see how deep that shaping truly went. This understanding became essential for preparing future missions to the Moon, to Mars, and eventually to more distant worlds. Every system that protects astronauts, stores resources, manages energy, or supports life must operate in conditions where weight is absent or drastically reduced. Microgravity experiments provided the knowledge needed to design these systems with confidence, ensuring that humanity could travel farther and stay longer in the harsh environment beyond Earth. As the second decade of the new century unfolded, the microgravity experiments aboard the International Space Station had grown from a handful of exploratory tests into a coordinated global effort to understand how gravity influences everything, from the flow of water to the drift of atoms. Each result became part of a larger story, a story that revealed the intimate connection between gravity and the very structure of the world. Microgravity taught us that gravity is not simply a background force, but a constant sculptor, silently shaping the behavior of matter at every moment. This quiet revelation changed the course of gravitational research. Scientists realized that to understand gravity fully, they could not rely solely on earthbound laboratories or theoretical equations. They needed the sky itself. The laboratory of orbit had shown that a universe free of weight looked different, felt different, and behaved differently in ways that were both mysterious and scientifically essential. Microgravity had opened the first door, revealing truths that Earth had kept hidden for 1,000 generations. And through that door, the next great chapters of gravitational exploration were waiting, stretching outward into the deep black of interplanetary space, where gravity would be tested on scales far greater than any orbit could provide. The moment a spacecraft escapes the boundaries of Earth orbit, it enters a realm where gravity begins to reveal a different face, one shaped by vast distances, shifting gravitational influences, and the intricate geometry of spacetime. Here, the pull of Earth fades into the background as the Sun becomes the dominant sculptor of motion. Beyond that, the gravitational fields of planets, moons, asteroids, and even the subtle pressure of sunlight contribute their influence. A spacecraft traveling through this enormous arena becomes a messenger from the deeper truth of gravity, carrying with it the imprint of every force and curvature it encounters. And as humanity learned to follow these paths with exquisite precision, gravity transformed from a familiar downward pull into a sweeping architecture stretching across the solar system. Interplanetary space is not empty. It is an environment shaped by the quiet tug of multiple bodies, each contributing to the overall curvature of space-time. When a spacecraft begins its journey away from Earth, it enters a region where its path is dictated not by fuel or engines, but by gravity itself. Once the rocket burns end and the engines fall silent, almost every movement becomes a conversation between mass and geometry. A probe coasts along a trajectory, calculated with incredible care, guided by the gravitational pull of the Sun and steered through careful encounters with planets. These gravitational assists, where a spacecraft swings close to a world to gain speed or change direction, are not acts of mechanical force. They are expressions of the geometry predicted by general relativity and refined through centuries of observation, calculations, and direct measurement. The earliest interplanetary missions revealed how sensitive these paths could be. The positions of planets had to be known with extraordinary accuracy, because even a small miscalculation could cause a spacecraft to miss its target by millions of kilometers. Engineers and scientists quickly learned that Newtonian physics, while powerful, needed the corrections predicted by general relativity to achieve the required precision. When a spacecraft passed near the Sun, for example, the curvature of spacetime altered the path of its radio signals. These signals took slightly longer to reach Earth, a phenomenon known as the Shapiro time delay. The effect was subtle, far too small to detect with traditional optical instruments, but measurable through the timing of radio communications. This delay matched the predictions of general relativity with remarkable precision, offering direct evidence for the theory far beyond the conditions found on Earth. Other relativistic effects also emerged. The bending of light, predicted by Einstein decades earlier, became a measurable influence on spacecraft communications. When the line of sight between a probe and Earth passed near the Sun, the curvature of spacetime caused the radio waves to bend slightly, altering the biased apparent position of the spacecraft. Even the slow precession of orbital paths predicted by general relativity, famously observed in the orbit of Mercury, became relevant as probes performed close passes around planets. These effects were not theoretical curiosities. They were practical necessities that engineers had to account for, because interplanetary missions depended on the faithful interpretation of every tiny shift in a probe's trajectory. The tracking of deep space missions became one of the most precise ways to test the predictions of gravity. Ground-based antennas measured the travel time of radio signals to and from spacecraft millions or even billions of kilometers away. These measurements revealed how gravity shaped motion on scales far larger than any laboratory could reproduce. When scientists followed the paths of the Pioneer probes, the Voyager probes, and later missions like Cassini and Juno, they saw gravity acting with consistent reliability. Every curve and deviation in the trajectory matched the combined influence of celestial bodies and the geometric corrections predicted by relativity. The solar system became a vast proving ground where gravity could be tested under conditions impossible to replicate on Earth. But these missions also exposed the challenges of exploring a universe governed by subtle forces. One of the most intriguing cases arose when the Pioneer probes appeared to slow down more than expected as they journeyed outward. For years, researchers debated whether this deceleration hinted at new physics or an unknown influence within the solar system. Careful analysis eventually revealed that the spacecraft themselves were the source. Heat emitted from their radioisotope generators created a faint recoil force, pushing the probes slightly backward. The effect was incredibly small, but measurable across billions of kilometers. This realization reinforced a crucial truth. In interplanetary space, understanding gravity requires an equally deep understanding of the spacecraft themselves. A tiny imbalance of heat or a slight change in surface reflectivity can mimic the influence of gravity if not accounted for with rigorous accuracy. As missions ventured farther, new forms of gravitational data emerged. The motion of the Voyager probes through the outer solar system provided insight into the distribution of mass beyond the orbit of Neptune. Cassini measured the gravitational field of Saturn and its moons with extraordinary detail, revealing ocean worlds hidden beneath icy crusts. Juno traced the deep interior currents of Jupiter by observing faint variations in its gravitational pull. Each mission became a tool, not just for exploring planets, but for mapping the invisible structures beneath their surfaces. Gravity became a probe, a subtle instrument capable of detecting mountains buried under ice, variations in planetary composition, and even the swirling motions of liquid metallic hydrogen deep within Jupiter. These interplanetary missions also deepened our understanding of how gravity shapes the flow of time. Atomic clocks on Earth and aboard satellites demonstrated that time passes at different rates depending on gravitational strength. Near massive bodies, time slows slightly. Farther away, it speeds up. This effect, predicted by general relativity, became essential for guiding deep space missions. When signals travel across immense distances, even a tiny difference in how clocks tick can cause significant errors in navigation. By accounting for these relativistic effects, scientists ensured that spacecraft followed their intended paths with astonishing accuracy. Through the steady accumulation of interplanetary data, the solar system became a laboratory for testing gravity across scales that ranged from the local pull of small moons to the vast influence of the Sun. Each mission confirmed that general relativity provided a consistent framework for understanding these phenomena, but they also revealed the limits of what could be studied within the solar system. Gravity remained reliable and predictable, yet questions lingered. What caused the invisible mass binding galaxies together? Why was the universe expanding faster over time? And how could the behavior of gravity at quantum scales be reconciled with its behavior across interplanetary distances? The answers to these questions lay beyond the orbit of planets, in the empty stretches of space where light from distant galaxies bent and stretched, and where the faint hum of gravitational waves rippled across spacetime. But before humanity could reach those frontiers, it first needed to understand gravity not as a force pulling objects downward, but as a universal influence shaping the motion of worlds. Interplanetary space became the bridge between the laboratory of microgravity and the vast cosmic stage where gravity would perform its most complex and mysterious roles. The deeper spacecraft traveled into the solar system, the more gravity revealed itself as a master sculptor, shaping everything from the faint drift of dust to the grand arcs of planetary motion. Interplanetary probes became silent witnesses to the invisible architecture that binds the solar system together. Their trajectories recorded faint gravitational whispers, small tugs and bends that carried the fingerprints of distant masses. Even the solar wind, a stream of charged particles flowing outward from the Sun, played its part by exerting a tiny pressure on spacecraft surfaces. Though far weaker than gravity, this pressure accumulated across long distances, requiring scientists to account for every detail if they wished to understand how gravity alone was guiding a probe's path. In this way, interplanetary exploration became not just a journey across space, but a deep interrogation of how mass and geometry control motion on scales far beyond anything Earth-based experiments could reveal. Each new mission offered a refined perspective. When the Voyager probes completed their grand tour of the outer planets, they carried with them data that reshaped our understanding of gravitational interactions in the outer solar system. As they passed Jupiter, Saturn, Uranus, and Neptune, the probes responded to the gravitational fields of these giant planets with exquisite sensitivity. Even slight variations in mass distribution beneath swirling atmospheres revealed themselves through tiny changes in the spacecraft's velocity. These changes were detected through radio signals whose timing accuracy reached fractions of a millisecond. Such precision allowed scientists to map the structure of planetary interiors indirectly, showing where dense regions of material lay hidden beneath clouds and storms. Gravity, acting through the probes, traced shapes that no telescope could ever see. Later missions, like Cassini, demonstrated how gravity could be used to explore an entire system of moons orbiting a gas giant. As Cassini flew past Saturn's moon Enceladus, slight deviations in its motion revealed that the moon was not solid throughout. Instead, it possessed a subsurface ocean of liquid water beneath its icy crust. The gravitational pull of Saturn and neighboring moons created slight oscillations in Enceladus' motion. Oscillations that Cassini could measure simply by monitoring how its radio signals shifted as it flew past. This was an extraordinary revelation. Gravity had turned into a tool for detecting oceans hidden beneath frozen surfaces, proving that gravitational measurements could reach into worlds and uncover secrets that telescopes could never observe directly. The Juno mission extended this approach to Jupiter. By entering a highly elliptical orbit, Juno allowed its instruments to detect subtle variations in Jupiter's gravitational field as it flew extremely close to the giant planet. These variations revealed that Jupiter's interior was not a simple layered sphere, but a fluid, dynamic region where enormous currents of metallic hydrogen circulated through a deep interior. The gravitational data showed how these flows created asymmetries, pulling the spacecraft slightly differently depending on where it passed. These differences, measured with scientific discipline and mathematical care, allowed researchers to build the most detailed model ever created of the interior of a gas giant. Gravity alone provided this map, proving once again that the invisible influence of mass and motion could reveal structures thousands of kilometers below surfaces that no human had ever seen. But gravity also played a critical role in understanding time itself during interplanetary missions. Atomic clocks aboard spacecraft and on Earth demonstrated that time flowed differently depending on distance from massive bodies. Near the Sun, time slowed. Farther away, it flowed slightly faster. Spacecraft traveling through these regions experienced these variations, and mission controllers corrected for them continuously. Without accounting for gravitational time dilation, the signals exchanged with interplanetary probes would drift out of sync, causing navigational errors that could grow dramatically over long journeys. This correction was not optional, it was essential, and it offered daily practical confirmation of general relativity using spacecraft flying through the very geometry that the theory described. The solar system also provided a natural arena for observing how gravity interacts with light. When signals from spacecraft passed near the Sun, their paths bent slightly and their travel times lengthened. These effects were predicted by general relativity and provided direct experimental confirmation every time a probe aligned itself with the Sun from Earth's perspective. Engineers planning communications windows for interplanetary missions knew that when a probe was on the far side of the Sun, radio signals would be delayed and distorted. This distortion was the curvature of spacetime expressed through the behavior of light itself. In this way, every mission became both a practical endeavor and an ongoing experiment in fundamental physics. Even the small bodies of the solar system revealed gravitational secrets. The way asteroids tugged on passing spacecraft exposed their mass and density. The complex orbital dance of moons around planets like Saturn and Jupiter displayed resonances predicted by gravitational theory. Comets followed elongated paths that recorded every influence they encountered. Each of these examples offered a piece of the grand puzzle. Gravity did not merely act on planets and stars. It also sculpted dust, guided icy fragments, and shaped the intricate ballet of small worlds orbiting the Sun. Interplanetary probes recorded these delicate influences, providing a detailed portrait of how gravity shapes systems large and small. At the same time, humanity learned that gravity was never alone in its task. Solar radiation pressure, though faint, pushed on spacecraft with cumulative force. Outgassing from heated materials created subtle thrusts. Even the reflection of sunlight from solar panels added small influences that could imitate gravitational effects, if not accounted for. The true challenge of interplanetary exploration lay not simply in understanding gravity, but in isolating its pure expression from all other forces. When this was achieved, data revealed how consistent and predictable gravity truly was. Every deviation that once puzzled researchers eventually yielded to careful analysis. The Pioneer anomaly, once a source of speculation, became a lesson in the meticulous accounting required to separate gravitational influence from the behavior of a spacecraft itself. Through all these missions, the solar system transformed into an immense physics laboratory. Each probe was a test mass drifting through the geometry of spacetime. Each radio signal was a measurement of gravitational curvature. Each slight deviation in motion was a message from the universe, telling scientists how gravity behaved across scales impossible to reach on Earth. As the data accumulated, one truth became clear. General relativity remained the best description of gravity, consistent across all distances and conditions encountered so far. Yet interplanetary missions also highlighted the limits of what could be measured within the solar system. There were hints of deeper mysteries, not in contradictions, but in the vastness of the cosmos, where invisible mass-shaped galaxies and the expansion of the universe accelerated for reasons still unknown. Interplanetary exploration revealed gravity as both sturdy and mysterious. It confirmed that the force guiding spacecraft was the same force shaping the motion of planets, bending the path of light, and influencing the flow of time. But it also hinted that gravity might be part of a larger story, one that could only be uncovered by looking beyond the boundaries of the solar system. The next steps in gravitational exploration would lead outward to distant galaxies, massive clusters, and the cosmic web itself, where the subtle interplay between mass and spacetime created patterns far beyond the reach of interplanetary probes. As the decades of interplanetary exploration unfolded, each mission revealed that gravity was not merely a force acting across empty space, but a grand architecture connecting every world, moon, and asteroid in a delicate and ancient design. The solar system, once imagined as a quiet void punctuated by planets, became an intricate stage where gravity choreographed a sprawling dance. This dance extended from the tight embrace of moons locked in resonance to the slow drift of distant bodies orbiting far beyond Neptune. Every movement in this vast network reflected the cumulative influence of mass distributed across millions of kilometers. Interplanetary missions became the first witnesses capable of recording this dance with the precision needed to understand its deeper meaning. One of the most striking examples of gravity's subtlety came from the orbital resonances observed among moons. Around Jupiter, for instance, several of the Galilean moons are locked in what is known as a Laplace resonance. For every 4 orbits of Io, Europa completes 2, and Ganymede completes 1. This precise ratio is not a coincidence. It is a product of gravitational interactions that occurred over countless ages. The moons continually tug on one another, nudging their orbits into exact alignments that persist across time. Spacecraft like Galileo and Juno measured these interactions through tiny changes in their own trajectories as they passed through Jupiter's complex gravitational field. Each shift, detected through radio signals received on Earth, offered a deeper glimpse into how gravity organizes entire systems of worlds with astonishing precision. The same gravitational relationships appear in the asteroid belt, where groups of asteroids align in patterns shaped by the pull of Jupiter. As these small bodies drift through the solar system, their paths are altered subtly by resonances. Some regions of orbit become crowded with asteroids, while others become empty gaps. These structures, known as Kirkwood gaps, were first predicted through gravitational calculations and later confirmed by observations. Interplanetary missions flying through the asteroid belt detected the distribution of these bodies, and measured the gravitational effects that created these patterns. Gravity had etched its logic into the belt, carving pathways and voids that reflected the deep harmony of celestial mechanics. As spacecraft pushed farther outward, they entered regions where the Sun's gravitational dominance began to fade. Beyond the orbit of Neptune, the influence of the Sun is still present, but weak enough that passing stars and the collective mass of the galaxy begin to play a measurable role. The Voyager probes recorded the subtle variations in the gravitational environment as they journeyed toward the edge of the heliosphere. While these effects were extremely small, they offered the first experimental hints that gravity transitions smoothly from the realm of planets to the broader influence of the galaxy itself. The solar system is not an isolated island. It is a node within a larger web of gravitational relationships extending across the Milky Way. Even comets, with their long elliptical paths, became teachers of gravitational truth. Their journeys carry them from the icy darkness of the outer solar system to the sunlit inner regions where they warm and shed material. These long arcs reflect every influence they encounter, from the pull of the planets to the faint gravitational tides of the stars. Missions like Rosetta, which orbited and landed on Comet 67P, Churyumov-Gerasimenko, showed how a small body, only a few kilometers wide, could still participate fully in the gravitational dance. Rosetta measured the comet's weak gravitational field directly, allowing scientists to calculate its density, internal structure, and mass distribution. This measurement revealed that even the smallest of worlds carries a gravitational signature shaped by its history. Gravity's subtle power also became evident in the way spacecraft use planetary encounters to alter their paths. These gravitational assists required exquisite accuracy. A probe passing a planet too closely or too far away would miss its intended destination by vast distances. Yet when executed correctly, these maneuvers transferred energy between spacecraft and planet without the use of fuel. This exchange illustrated a profound principle. Gravity is not a force that simply pulls. It also shapes the flow of energy and momentum across space. A single encounter could change a spacecraft's speed or direction by tens of thousands of kilometers per hour, all without a single burst of fuel. These maneuvers were demonstrations of the elegance and efficiency of celestial mechanics, revealing that gravity is as much a sculptor of motion as it is a guiding influence. At the same time, interplanetary missions illuminated the challenges of navigating a universe where gravity is only one part of a larger equation. Solar radiation pressure, though faint, continuously pushed against spacecraft. Dust particles drifting through space occasionally struck their surfaces, imparting tiny impulses. Even the thermal radiation emitted by a spacecraft's electronics created minute forces that altered its path. To isolate the pure effect of gravity, scientists had to account for all these influences meticulously. Every mission became a lesson in precision, demonstrating that understanding gravity required careful control of everything that could mimic its influence. When these factors were accounted for, gravity remained consistent, predictable, and aligned with the predictions of general relativity. The more data accumulated, the more scientists realized that the solar system itself could not answer every gravitational question. It confirmed that Einstein's theory provided accurate predictions across a wide range of conditions. It revealed how gravity sculpted planetary interiors, guided moons into resonances, and controlled the trajectories of spacecraft. But the solar system did not contain the extreme environments needed to test gravity under the most intense conditions. There were no supermassive black holes nearby, no collapsing neutron stars emitting ripples of gravitational waves, and no cosmic structures large enough to reveal the role of dark matter on billion-kilometer scales. The solar system was a precise and detailed laboratory, but it was still limited. To explore the deeper mysteries of gravity, humanity would need to look beyond the planets, toward the vast structures that shape the universe. Even so, the interplanetary missions had accomplished something extraordinary. They had turned the solar system into a map of gravitational truth. capturing the interplay of forces across distances and scales previously unimaginable. They had demonstrated that gravity remains consistent from the surface of Earth to the outer edge of the heliosphere. They had shown that even the faintest gravitational signals can be measured with careful instrumentation, and they had prepared the scientific community to confront the larger mysteries waiting in the cosmos. With each probe launched into the deep, humanity stepped closer to answering some of the most profound questions ever asked. What holds galaxies together? What drives the expansion of the universe? And how does gravity connect the grand structure of space-time to the invisible world of quantum physics? These questions lay beyond the interplanetary frontier, waiting in the silent stretches of space where gravity becomes both the storyteller and the story itself. There are moments when the universe reveals something so unexpected that it reshapes the direction of science for generations. These revelations rarely come through dramatic explosions or sudden events. Instead, they arrive quietly, as faint lines of starlight passing through telescopes, as gentle distortions in the shapes of galaxies, as temperature patterns frozen into the ancient afterglow of the cosmos. The invention of space-based observatories opened a new chapter in the study of gravity, because for the first time, humanity could see the universe without the blur of Earth's atmosphere. In that clarity, gravity exposed the presence of something vast and invisible, something that guided the motion of galaxies and shaped the universe on its largest scales. This was the beginning of the discovery of the dark universe. Before the launch of the first space telescopes, astronomers had long suspected that the universe contained more mass than the stars and gas they could observe. Galaxies rotated too quickly, as though pulled by an invisible presence. Clusters of galaxies held together with a strength that visible matter alone could not explain. These observations hinted that a hidden form of matter must exist, one that did not reflect or absorb light, but still possessed mass. This unseen substance became known as dark matter. For decades, Earth-based telescopes collected data supporting its existence, but the atmosphere distorted the incoming light and limited the precision of observations. The arrival of space observatories changed everything. Freed from atmospheric turbulence, instruments could now detect the faint bending of light caused by massive objects, providing direct and unmistakable evidence for the dark matter that silently threaded the universe together. The Hubble Space Telescope became one of the most important tools in this effort. When it began capturing images of distant galaxy clusters, astronomers noticed arcs and streaks of distorted light surrounding them. These arcs were not artifacts or errors. They were the result of gravitational lensing, a phenomenon predicted by general relativity. Massive clusters bend the path of light passing near them, creating a natural lens that magnifies and distorts background galaxies. By measuring the amount of bending, scientists could map the distribution of mass within the cluster. Again and again, the maps showed the same result. Most of the mass was invisible. It did not emit light. It did not reflect light. It revealed itself only through gravity. These gravitational lensing observations from Hubble provided some of the strongest and most direct evidence for dark matter ever collected. But dark matter was only half of the dark universe story. As astronomers refined their measurements of distant exploding stars known as Type 1a supernovae, they discovered something even more astonishing. The expansion of the universe was not slowing down under the pull of gravity as expected. It was speeding up. The light from these supernovae showed that distant galaxies were accelerating away from one another at an increasing rate. This observation, confirmed by multiple space-based instruments, revealed that some form of energy permeated the universe, driving its expansion faster and faster. This mysterious influence became known as dark energy. Its discovery reshaped cosmology completely, extending the puzzle of gravity far beyond what Einstein or Newton ever envisioned. To understand this accelerating universe, scientists turned to observations of the cosmic microwave background, the faint afterglow left behind by the birth of the universe. Space missions like the Wilkinson Microwave Anisotropy Probe, often called WMAP, and later the Planck spacecraft mapped this radiation with extraordinary sensitivity. Their maps revealed tiny temperature variations across the sky, patterns that recorded the early distribution of matter and energy. By analyzing these patterns, scientists could measure the total amount of ordinary matter, and dark energy present in the universe. The results were astonishing. Ordinary matter, the stars, planets, gas, and dust that make up everything familiar, accounted for only a small fraction of the total cosmic content. Dark matter contributed far more, and dark energy dominated the entire structure and fate of the cosmos. These findings were not speculative. They were grounded in precise measurements of radiation, gravitational lensing, galaxy clustering, and supernova brightness. Together, they formed a consistent and compelling portrait of the universe. Dark matter shaped the skeleton of cosmic structure, guiding the formation of galaxies and the arrangement of clusters. Dark energy controlled the expansion of the universe, pushing galaxies apart at an accelerating rate. Gravity responded to both, curving spacetime according to their combined influence. In this way, gravity became a messenger, revealing the presence of phenomena that could not be detected through light alone. The success of space observatories did not come solely from their ability to escape the atmosphere. It came from the stability and clarity they provided. Telescopes in orbit could observe the same region of the sky for hours or days without interruption. They could detect faint signals lost in the glare of Earth-based light pollution. They could measure subtle distortions in the shapes of galaxies, revealing the unseen structures surrounding them. This stability allowed missions like Hubble to observe distant galaxies with unparalleled detail, and missions like Planck to map the cosmic microwave background with precision that could not be matched from the ground. As new observatories joined the effort, the picture became even clearer. Instruments aboard the James Webb Space Telescope captured detailed infrared views of early galaxies, providing new data on how structure formed in the first few 100 million years after the universe began. Europe's Euclid mission focused on mapping the distribution of dark matter and dark energy across vast cosmic distances, using gravitational lensing and galaxy clustering to trace the invisible scaffolding of the universe. Each of these missions added new layers of evidence, revealing a universe far more complex than what had been imagined during the early days of astronomy. Gravity, once a force familiar from falling apples and orbiting planets, had become the key to unlocking the structure of the cosmos. The observations collected by space telescopes showed that gravity responds to all forms of mass and energy, visible or invisible. It bends light, shapes galaxies, and influences the expansion of the universe. Through the lens of these observatories, gravity revealed the presence of dark matter pulling on stars and clusters, and dark energy stretching the fabric of space-time itself. The universe was no longer understood solely through visible light. It had become a gravitational tapestry, woven from forces seen and unseen, each playing a role in shaping the cosmos we inhabit. Yet these discoveries, profound as they were, also raised new questions. What is dark matter made of? Why does dark energy accelerate the expansion of the universe? And how does gravity connect to these mysterious phenomena? These questions lay beyond the reach of Earth-based laboratories and required observations from the silent vantage point of space. The next steps in gravitational exploration would depend on the continued evolution of space observatories, each designed to peel back another layer of the cosmic mysteries that gravity had so elegantly revealed. As space observatories gathered more images, more spectra, and more subtle distortions in the shapes of distant galaxies, the universe began to look less like a simple collection of stars, and more like a vast and intricate structure shaped by forces invisible to the eye. With every new observation, gravity revealed that the cosmos was built upon hidden foundations. Dark matter formed invisible halos around galaxies, drawing stars into spirals and holding clusters together with a strength far beyond what visible mass could provide. Dark energy stretched space so gently and yet so relentlessly that the expansion of the universe grew faster with time. These revelations did not replace gravity or contradict it. Instead, they showed that gravity was the only reliable guide for detecting the parts of the universe that could not be seen directly. The more detailed the observations became, the more clearly the cosmic web emerged. Space observatories created maps showing that galaxies were not scattered randomly across the sky. Instead, they traced enormous filaments of dark matter stretching across billions of light years. These filaments connected clusters in a delicate network resembling strands of frost on a window pane. Gravity shaped these structures over billions of years, pulling matter together into long chains and leaving vast empty regions in between. From Earth, this pattern was impossible to see because the atmosphere blurred the details. But telescopes in orbit observed the faint stretching of background galaxies caused by the gravitational influence of these dark filaments. This stretching, known as weak lensing, allowed scientists to map the invisible with remarkable accuracy. Weak gravitational lensing became one of the most powerful tools in modern cosmology. It depended not on the brightness of galaxies or the presence of gas, but on the subtle way gravity bent the paths of light. By measuring these distortions across millions of galaxies, astronomers could reconstruct the distribution of dark matter throughout the universe. Space-based observatories made this process far more precise, because their images were not distorted by the turbulence of Earth's atmosphere. The shapes of distant galaxies were captured cleanly, allowing faint gravitational signatures to stand out. These measurements confirmed that dark matter dominated the formation of structure in the universe and that it provided the gravitational scaffolding upon which galaxies assembled. Another breakthrough came from studying the most distant galaxies visible in infrared light. Observations from the James Webb Space Telescope revealed early galaxies forming when the universe was only a small fraction of its current age. These young galaxies were surrounded by halos of dark matter that guided the flow of gas into dense regions where stars ignited. Without dark matter, these early galaxies could not have formed so quickly. The gravitational pull of the invisible halos accelerated the collapse of gas, allowing star formation to begin less than 1 billion years after the birth of the universe. Webb's infrared vision, unobstructed by Earth's atmosphere, allowed astronomers to observe these early structures with clarity that had once seemed impossible. These observations tied the formation of the first galaxies directly to the gravitational influence of dark matter. While dark matter shaped the structure of the universe, dark energy shaped its evolution. Observations from space telescopes revealed that galaxies were not simply drifting apart. They were accelerating away from one another. The cause was not visible. It could not be detected through light or radiation. Yet its influence appeared in the brightness and redshift of distant supernovae, in the patterns of the cosmic microwave background, and in the distribution of galaxies across cosmic time. Dark energy remained a mystery, but space observatories allowed scientists to measure its effects with increasing precision. By comparing observations of distant galaxies with models of cosmic expansion, researchers developed a timeline showing how dark energy grew dominant as the universe expanded. Gravity responded to this influence, curving spacetime in ways that matched the accelerating expansion observed through telescopes. One of the most remarkable achievements of space-based cosmology was the creation of a detailed timeline of the universe. This timeline showed how matter and energy shaped cosmic evolution from the first fraction of a second after the universe emerged to the formation of galaxies, stars, and planets. The cosmic microwave background revealed the earliest conditions, with tiny fluctuations that later grew into galaxies. Observations of distant clusters mapped the development of large-scale structure. Measurements of supernovae captured the acceleration of cosmic expansion. Together, these data formed a coherent picture. The universe began hot and dense, expanded and cooled, formed structures under the influence of gravity, and then entered an era where dark energy took over, causing expansion to speed up. Every step of this process was grounded in evidence collected by space observatories. Even as this picture grew clearer, mysteries remained. What particles made up dark matter? Why did dark energy exist at all? Was it a property of space-time itself, or a sign of new physics waiting to be discovered? These questions could not be answered with Earth-based instruments alone. They required deep observations, long exposures, and measurements across enormous distances. Space observatories provided these capabilities. Missions like Euclid were designed to map billions of galaxies, tracing the evolution of cosmic structure with unprecedented accuracy. The Nancy Grace Roman Space Telescope would search for signatures of dark energy using multiple independent techniques, reducing uncertainties and testing the limits of current cosmological models. Each mission represented another step toward understanding the unseen forces shaping the universe. Through all these discoveries, gravity remained the guide. It bent light, shaped galaxies, and revealed the hidden components of the cosmos. It allowed scientists to detect dark matter not by observing the matter itself, but by observing its effects. It made dark energy visible not through direct detection, but through its influence on the expansion of space-time. In this sense, gravity became the language of the universe, spoken across distances so vast that light alone could not tell the full story. Space observatories translated this language into maps, measurements, and patterns that scientists could study and understand. Yet the more the universe revealed, the more profound the questions grew. If dark matter shaped cosmic structure, what was its true nature? If dark energy drove the expansion of the universe, what did this say about the future? Would expansion continue forever, stretching galaxies until they drifted beyond one another's reach? Or would some deeper influence emerge, altering the trajectory of cosmic evolution? These questions hinted at chapters still unwritten, chapters that would require new instruments, new ideas, and new ways of observing gravity on scales even larger than before. Space observatories had shown that the universe was far more complex than the visible stars suggested. They had revealed the dark scaffolding holding galaxies together and the mysterious energy pushing them apart. But they had also shown that the universe was open to discovery, that its deepest secrets could be uncovered through patient observation and the careful interpretation of gravity's subtle signals. The journey into the dark universe had begun, but it was far from complete. As the era of space-based astronomy matured, the universe appeared less like a quiet expanse and more like a living structure, shaped by forces that rarely revealed themselves directly. The stars and galaxies people once believed were the primary actors in the cosmic story turned out to be only the luminous surface of a much deeper architecture. Dark matter and dark energy were not temporary hypotheses. They were essential components woven into the fabric of space-time, shaping the universe from its earliest moments to its distant future. And while Earth-bound telescopes had provided hints, it was only through observatories placed above the atmosphere that humanity saw the evidence clearly, stripped of distortion and amplified by the precision of instruments suspended in quiet orbit. One of the most transformative insights of this era came from the realization that gravitational lensing did more than reveal the shapes of distant galaxies. It allowed scientists to measure how dark matter evolved over time. When astronomers compared lensing maps created from galaxies at different distances, they saw the growth of structure across billions of years. In the early universe, matter clumped together slowly, forming faint filaments and small halos. As time passed, these structures merged into larger and more complex formations. Space telescopes detected this evolution by observing how gravitational lensing signatures changed with cosmic age. This created a time-lapse portrait of the universe, showing how dark matter guided the assembly of galaxies and clusters, and how gravity sculpted the cosmic web one filament at a time. These gravitational maps also revealed a subtle tension. When compared to predictions from mathematical models, the observed distribution of dark matter suggested that structures might have formed slightly slower than expected. This discrepancy too small to overturn current theories, nonetheless hinted that there might be more to gravity than the current equations revealed. It did not contradict general relativity, but suggested that the story of the universe could carry layers still invisible to observation. Space observatories continued to refine these measurements, searching for clues that might point toward new physics. Yet the data always returned one message clearly. Whatever dark matter and dark energy were, they shaped the universe through gravity, and gravity remained the interpreter of their hidden roles. The cosmic microwave background deepened this picture further. When the Planck spacecraft mapped the faint microwaves left behind from the early universe, it found tiny variations in temperature and polarization that encoded the seeds of cosmic structure. These patterns showed where dark matter began to gather, where ordinary matter followed, and how gravity pulled both together in a slow, majestic process that lasted billions of years. By analyzing these variations with extraordinary precision, scientists determined the age of the universe, the curvature of spacetime on the largest scales, and the relative amounts of ordinary matter, and dark energy. The results painted a remarkably consistent picture. Dark matter provided the gravitational foundation, dark energy controlled the expansion, and gravity guided the growth of cosmic structure from the first moment to the present. While these discoveries answered many questions, they also sharpened others. What exactly creates the gravitational pull attributed to dark matter? What physical process drives dark energy? And how can gravity operate so consistently across such vast distances when its behavior at quantum scales remains unknown? These questions brought cosmology and fundamental physics closer together than ever before. They showed that understanding the universe required not only better telescopes, but also deeper theories capable of connecting the largest structures in the cosmos to the smallest particles in existence. The search for answers led to new observational strategies. Astronomers studied galaxy clusters, the largest gravitationally bound structures in the universe, to understand how dark matter shaped their formation. They examined the way galaxies within these clusters moved, revealing mass far beyond what was visible. They also used gravitational lensing to create detailed maps of how dark matter was distributed inside the clusters themselves. One of the most striking examples came from observing colliding galaxy clusters, such as the famous Bullet Cluster. In this system, galaxies pass through one another with little interaction, but the ordinary matter, consisting mostly of hot gas, collided and slowed. Dark matter, however, appeared to continue moving nearly undisturbed. The separation between the distribution of ordinary matter and dark matter provided some of the clearest evidence that dark matter was not made of gas or stars, but of something fundamentally different, something that interacted primarily through gravity. Space-based telescopes were essential in studying such systems. Their sharp vision captured the gravitational lensing signatures needed to separate the distributions of visible and invisible mass. Without this clarity, the faint distortions that revealed the location of dark matter would have been lost within the blur of Earth's atmosphere. The Bullet Cluster became a turning point, a demonstration that space observatories were not merely improving astronomy, but fundamentally transforming it. They provided measurements that disciplines like particle physics could not supply. They offered real, independent confirmation that dark matter was not an illusion or a misunderstanding of gravity, but a genuine component of the cosmos. As these observations accumulated, new tensions appeared, not as contradictions, but as invitations to look deeper. Measurements of the rate of cosmic expansion, known as the Hubble constant, began to differ depending on whether they were derived from local universe observations or early universe measurements from the cosmic microwave background. This discrepancy became one of the most important questions in modern cosmology. Was it a sign of new physics, or a consequence of unknown complexities in the data? Space observatories played a central role in exploring these differences, providing precise measurements that formed the foundation for every analysis. The existence of this tension revealed that even with the most accurate instruments, the universe still held secrets not yet understood. Through all of this, gravity remained the central guide. Its influence shaped the light captured by telescopes, dictated the motion of galaxies, and encoded the history of the cosmos in patterns stretching across billions of years. The discoveries made by space observatories showed that to understand gravity fully, one had to observe it in action across the entire universe. The solar system offered insights into how gravity acted on planets and moons. Microgravity experiments revealed how gravity shaped matter in subtle ways. Interplanetary missions tested gravity across millions of kilometers. But it was the vast expanse of the cosmos that revealed gravity's deepest roles, connecting the structure of galaxies to the evolution of spacetime itself. By the end of this era, one truth had become clear. The universe was far more than the stars that filled the sky. It was a dynamic, expanding, interconnected structure built upon gravity and shaped by forces still waiting to be fully understood. Space observatories had illuminated this structure with remarkable clarity, creating a foundation upon which the next generation of missions would build. They had shown that gravity does not merely govern motion, it reveals the unseen. It connects the visible and the invisible. And through it, the universe had begun to tell its story, one subtle distortion and faint signal at a time. Long before humanity understood the vast scale of the dark universe, scientists sought a more intimate goal: to measure gravity with a level of precision that Earth itself could not support. Gravity is the weakest of the known fundamental interactions, so faint that even a small gust of wind or a shift in the ground can overwhelm the delicate signals scientists try to observe. On Earth, vibrations from ocean waves, distant earthquakes, and even passing vehicles ripple constantly through the crust. Air currents stir, temperatures fluctuate, and instruments drift by imperceptible amounts. These disturbances make precise gravitational measurements extraordinarily difficult. But once satellites began to orbit above these disturbances, a new era of measurement began, one that revealed subtle motions of Earth, the shifting of oceans, and even tiny changes in the distribution of ice across continents. The Gravity Recovery and Climate Experiment, known as GRACE, became one of the most groundbreaking missions in this arena. Launched into orbit, the mission involved two satellites chasing one another across the sky, separated by a distance of a few hundred kilometers. Their job was deceptively simple. Each satellite constantly measured the distance between itself and its partner. As they passed over regions of Earth with slightly stronger or slightly weaker gravitational pull, their separation changed by minute amounts. One satellite would accelerate or decelerate relative to the other, responding to variations in Earth's gravitational field caused by mountains, valleys, underground water, or shifting ice sheets. By tracking these tiny changes in separation with exquisite precision, GRACE created detailed maps showing how mass moved across the planet over time. It captured seasonal changes in water storage, the thinning of ice sheets in Greenland and Antarctica, and the gradual rebound of land once compressed by ancient glaciers. These measurements were impossible to perform from Earth because the signals were far too faint. Only in orbit, where satellites could glide smoothly through microgravity, free from atmospheric drag and seismic noise, could such precision be achieved. The follow-up mission, GRACE Follow-On, continued this work with improved technology, demonstrating that satellites could become instruments of nearly unimaginable sensitivity. They measured changes so small that they corresponded to the movement of water amounts far below what any surface-based instrument could detect. Gravity, once seen as a simple downward pull, became a tool for observing the heartbeat of the planet itself. Another set of missions focused on a very different aspect of gravity: the slow twisting of space-time caused by the rotation of massive bodies. This effect, known as frame dragging, was predicted by general relativity, but had never been measured directly with the precision required to confirm it fully. The laser geodynamic satellites, known as LAGEOS, were among the first to tackle this challenge. These satellites were essentially spherical reflectors covered in tiny mirrors. Astronomers on Earth directed powerful laser pulses toward them, and the satellites reflected the pulses back. By measuring the round-trip time to extraordinary accuracy, scientists could track the satellite's orbits with remarkable precision. Over long periods, they detected tiny shifts in these orbits, caused by the spinning Earth dragging spacetime slightly along with it. This measurement, though subtle, provided crucial confirmation of a prediction at the heart of general relativity. Later, Gravity Probe B carried this effort even further. It used some of the most precise gyroscopes ever created to measure how spacetime curves and twists around Earth. Each gyroscope floated in a vacuum chamber aboard the spacecraft, spinning freely and without friction. Any tiny change in the direction of the gyroscope's axis revealed the influence of spacetime curvature. Over the course of the mission, the gyroscopes recorded changes so small that they would have been drowned in noise on Earth. Their measurements provided another confirmation of the geodetic effect and frame dragging, showing that Einstein's predictions extended even to the gentle swirl of spacetime around a single planet. At the same time, lunar laser ranging experiments offered a way to test gravity across nearly 400,000 kilometers. Reflectors left on the Moon's surface during the Apollo missions allowed scientists to bounce laser pulses off them and measure the round-trip travel time. The precision reached by these experiments became so high that even the tiny shift in the Moon's orbit caused by tidal interactions and gravitational influences could be measured year by year. These observations placed stringent limits on any deviation from general relativity. If gravity behaved differently at the scale of the Earth-Moon system, these measurements would have revealed it. Instead, they confirmed once again that general relativity remained consistent across the distances humanity had explored so far. Orbital atomic clocks added another layer to this story. Time itself flows differently in regions of different gravitational strength. Near a massive body, time slows slightly, while farther away it runs faster. This effect, called gravitational time dilation, is one of the central predictions of general relativity. Satellites carrying precise atomic clocks allowed scientists to test this prediction directly. By comparing the ticking rates of clocks on Earth with those aboard satellites, researchers observed the exact amount of time dilation predicted by Einstein's equations. This was not a subtle or ambiguous effect. It had to be accounted for every day to keep global navigation systems accurate. Without correcting for gravitational time dilation, the position information provided by satellite-based systems would drift by kilometers each day. Gravity, as predicted by relativity, shaped the flow of time in ways that satellites made impossible to ignore. Another remarkable mission tested one of the deepest principles of gravity, the equivalence principle, which states that all objects fall at the same rate in a gravitational field, regardless of their mass or composition. The microscope mission placed pairs of test masses in orbit and allowed them to drift freely inside a satellite. By measuring their motion with astonishing precision, scientists sought any sign that different materials might fall at different rates. Such a discovery would have challenged the foundation of general relativity and opened the door to new theories. Instead, microscope confirmed the equivalence principle to unprecedented accuracy, showing once again that gravity acted uniformly across materials and masses, even under the pristine conditions of orbit. Through all these missions, a clearer picture emerged. Gravity was not simply a background force. It was a measurable, dynamic presence, shaping the flow of time, guiding the paths of satellites, and revealing hidden structures beneath Earth's surface. Each new technology sharpened humanity's ability to observe its influence. Scientists learned that even the faintest gravitational signals carried information about the environment they passed through. Changes in water storage across a continent, the spin of Earth, the curvature of spacetime, and the structure of the Moon's orbit all became measurable through gravitational effects alone. These precise measurements transformed gravity into an instrument as well as a phenomenon. It became a means of observing Earth's interior, monitoring climate processes, testing fundamental physics, and guiding the navigation of spacecraft across millions of kilometers. Orbiting instruments achieved what Earth-based laboratories could not. They removed the noise, eliminated the shaking ground, and allowed gravity to speak in its purest form. With each mission, the universe revealed its structure a little more clearly, showing that gravity is not merely a constraint, but a tool for discovery, a window through which scientists could peer into the hidden workings of both Earth and the cosmos. The deeper scientists pushed into the domain of precision gravitational measurement, the more they realized that gravity was not only a force shaping the motion of planets and the curvature of space-time, it was also a quiet storyteller, encoding information about every layer of Earth, every orbit of the Moon, and every shift in the distribution of mass across land and sea. Satellites and spaceborne instruments transformed gravity into a method of observation, revealing processes that could never be detected from the ground. As missions collected more data, gravity seemed less like a passive pull and more like a woven record of change, responding to water flow, glacier loss, mantle motion, and even the slow drift of continents as Earth continued its ancient geological dance. One of the most moving examples of this transformation came from the way Grace observed Earth's water cycle. Rivers rose and fell with the seasons, groundwater layers expanded and contracted, and monsoon rains drenched entire regions before retreating. Each of these changes involved shifts in the distribution of mass, and every shift produced a signal that gravity quietly recorded. Grace traced these changes with an elegance no Earth-based system could match. It showed how drought drained underground reservoirs across large regions, how melting snowpacks altered the gravitational field of entire mountain ranges, and how shifts in ocean currents created patterns in the sea level that could only be understood through precise gravitational mapping. These discoveries turned gravity into a global environmental tool, allowing scientists to monitor changes with a clarity once thought impossible. As researchers studied the data, they began to see patterns linking gravitational shifts to the interior dynamics of Earth. The crust rose slowly in regions where glaciers had melted, a rebound that began thousands of years ago when the last ice age ended. The mantle flowed beneath the crust with a slow, steady motion, redistributing mass over centuries. These gradual changes, far too subtle to observe directly, appeared in gravitational measurements as faint but persistent signals. Over time, satellites revealed how Earth's interior breathed and shifted, responding to processes that unfolded on geological timescales. Gravity, measured with precision, became a tool for understanding the living Earth from its surface to its deep interior. But the precision of these space-based instruments also demanded a deeper understanding of the forces acting on satellites themselves. Every tiny influence mattered. The slight drag from Earth's upper atmosphere could shift an orbit. The faint push from sunlight reflecting off a satellite's surface could accumulate over time. Even the heat emitted by the spacecraft could create a subtle recoil. Engineers quickly learned that to measure gravity accurately, they had to understand and control every non-gravitational effect. This attention to detail reflected the discipline required to study a force so faint that even the smallest disturbance could blur its signature. Only by removing these influences could the pure effect of gravity emerge, revealing its structure with clarity. These challenges also inspired new methods of spacecraft design. Satellites intended for precision gravitational measurement were built to minimize unwanted forces. Their surfaces were designed to reduce sunlight pressure. Their shapes were chosen to avoid uneven heating. Their movements were controlled by systems that compensated for tiny accelerations, allowing them to drift as freely as possible. This approach created an environment where satellites behaved like perfect test masses, responding only to gravity. In this way, each satellite became not just an instrument, but a participant in an experiment, drifting through orbit in a controlled fall that allowed gravity to reveal its secrets. The ability to measure gravity with such precision also opened the door to deeper tests of general relativity. The theory predicted exactly how space-time should curve around Earth, how the Moon's orbit should evolve, and how time should flow at different altitudes. Space-based measurements allowed scientists to test these predictions across scales impossible on the ground. lunar laser ranging confirmed that the Earth-Moon distance increased gradually each year due to tidal interactions. Time dilation measurements from atomic clocks demonstrated that clocks in higher orbits ticked faster, exactly as predicted. Frame dragging measurements revealed that Earth's rotation twisted spacetime slightly. Each of these observations strengthened the evidence for general relativity, showing that the theory held true even under conditions that Einstein himself could only imagine. Yet these successes also exposed the growing need for even more sensitive instruments. As cosmological observations revealed the existence of dark energy and dark matter, scientists realized that gravity needed to be measured across both larger and smaller scales. Understanding these mysterious components required instruments that could detect even finer variations in gravitational fields. Proposals for future missions grew more ambitious. Some missions aimed to study gravitational waves from orbit, using spacecraft separated by millions of kilometers. Others envisioned new generations of satellites capable of measuring Earth's changing mass distribution with even greater sensitivity. These ideas were not futuristic fantasies, but logical extensions of the techniques already proven by missions like GRACE, LAGIOS, and Gravity Probe B. As the data accumulated, the relationship between gravity and time became especially important for deep space navigation. Every probe traveling toward Mars, Jupiter, or beyond depended on accurate timing to determine its position. Even a tiny difference in the speed of a clock could cause a spacecraft to drift off course over millions of kilometers. The realization that time itself flowed differently depending on gravity was no longer an abstract insight. It became a practical necessity, integrated into the daily operations of space missions. In this way, general relativity moved from the chalkboards of physics classrooms into the heart of space exploration technology. The precision enabled by these orbital measurements also allowed scientists to refine the value of fundamental constants related to gravity. The gravitational constant, long known for being difficult to measure accurately on Earth, could be tested indirectly through observations of planetary motion and spacecraft trajectories. These measurements reduced uncertainties and allowed models of the solar system to be computed with stunning accuracy. This, in turn, improved predictions of planetary positions, the behavior of satellites, and even the long-term stability of the solar system's architecture. Through all these advances, one idea grew steadily clearer. Gravity is not a simple force. It is a record keeper, a storyteller, a silent witness to the movement and transformation of matter across scales ranging from underground water layers to entire planets. It leaves signatures everywhere, waiting only for instruments sensitive enough to detect them. Space, with its quiet and stable environment, provided the vantage point needed to read these signatures. Orbit became not only a platform for exploration, but a laboratory where gravity could be studied with a purity impossible on Earth. The growing precision of gravitational measurements prepared scientists for the next chapter of exploration, one in which gravity would no longer be observed indirectly. Soon, humanity would listen to gravity itself, hearing the ripples of space-time generated by cataclysmic cosmic events. Before that era arrived, the work of satellites and orbital instruments had built a foundation of understanding. They had taught humanity how gravity behaves around Earth, how it shapes motion, and how it responds to the distribution of mass. This foundation made it possible to recognize what came next: the discovery of gravitational waves, the sounds of space-time itself echoing across the cosmos. The more precisely scientists measured gravity from orbit, the clearer it became that this quiet force was an ever-present companion, responding instantly to every shift in the distribution of mass, both on Earth and throughout the solar system. It guided spacecraft, shaped the flow of time, revealed hidden changes beneath Earth's surface, and maintained a silent balance between celestial bodies. Yet the more scientists refined their measurements, the more they sensed an approaching threshold. Gravity's familiar behavior, mapped so thoroughly across Earth and among the planets, hinted at phenomena waiting just beyond the reach of traditional instruments. Everything learned so far pointed toward a universe where gravity carried not only the marks of mass and curvature, but also the echoes of distant, powerful events. Before reaching that threshold, however, scientists had to understand gravity in its most refined, most controlled form. That journey continued with increasingly sensitive missions, each designed to remove interference until only the pure expression of gravity remained. One of the most remarkable examples of this precision came from long-term tracking of Earth's rotation and orientation. Satellites equipped with laser reflectors and radio beacons observed the slight wobble in Earth's spin. Tiny shifts caused by the movement of mass within the mantle, changes in atmospheric winds, and variations in ocean currents. These wobbles were measured with such fidelity that scientists could detect seasonal changes in wind patterns by observing minute variations in the length of a day. These variations amounted to fractions of milliseconds, far too small for ordinary clocks, yet unmistakable in the gravitational influence they produced. The planet's rotation was not fixed. It breathed and oscillated subtly, and gravity offered a way to observe these motions with astonishing clarity. The use of satellite-based accelerometers pushed this precision even further. Accelerometers sensitive enough to detect minute forces allowed spacecraft to account for all non-gravitational influences acting upon them. When an accelerometer measured a small push from sunlight or a faint atmospheric drag, that force could be subtracted from the satellite's motion, leaving only the gravitational component behind. This method created what scientists called a drag-free environment, where the satellite corrected its own position to ensure it drifted along the pure curve of spacetime shaped by Earth. These drag-free systems became essential in missions designed to test aspects of general relativity and to prepare for future gravitational wave observatories that would depend on nearly perfect isolation from external forces. At the same time, gravity remained a powerful tool for studying Earth's evolving climate. By examining changes in the gravitational field, scientists tracked the melting of polar ice with unprecedented accuracy. The loss of ice mass in Greenland and Antarctica produced measurable reductions in gravitational strength over those regions, while the redistribution of water across the planet created complementary increases elsewhere. Grace follow. ON captured these changes year after year, creating a continuous record of Earth's shifting mass. This dataset became one of the most important indicators of global climate trends, offering direct evidence of glacial melt and groundwater depletion. Through gravity, scientists saw not only where water flowed, but also how climate patterns were reshaping the physical structure of the planet. Similarly, the study of ocean dynamics benefited from these gravitational measurements. Currents in the oceans move enormous quantities of water, and these movements subtly alter the gravitational field. By combining satellite altimetry with precise gravity measurements, scientists observed how ocean circulation patterns evolved. The rise and fall of sea levels, driven by both thermal expansion and the movement of water masses, left gravitational fingerprints that allowed researchers to reconstruct regional and global changes. These observations revealed how the oceans absorbed heat, redistributed energy, and interacted with atmospheric systems. Gravity had become a tool not just for studying the Earth below, but for understanding the fluid systems that covered its surface. The gravitational connection between Earth and the Moon continued to serve as another arena for precision measurement. Lunar laser. Ranging experiments refined the understanding of the Moon's internal structure, revealing how its core, mantle, and crust interacted gravitationally with Earth. These measurements confirmed that the Moon was slowly drifting away from Earth, a consequence of tidal interactions that transferred angular momentum from Earth's rotation to the Moon's orbit. This drift, only a few centimeters each year, was measured with accuracy reached through decades of laser ranging. Such precision would have been unimaginable without space-based reflectors and orbital instrumentation. Gravity offered a way to observe the long-term evolution of the Earth-Moon system, revealing a relationship shaped by billions of years of mutual influence. While these Earth and lunar measurements continued to refine the understanding of gravity's behavior in familiar settings, The next frontier lay in preparing for instruments capable of detecting gravity in entirely new forms. The success of missions like Gravity Probe B and GRACE demonstrated that spacecraft could achieve the necessary stability for far more ambitious observations. Scientists began designing experiments that would place test masses in even quieter environments, shielded from disturbances and separated by vast distances. The goal was to observe how gravity behaved when space itself shifted in response to enormous cosmic events. These future missions would rely on the same principles refined through earlier satellite missions, but scaled up to unprecedented precision. This preparation reflected a growing realization. The universe was filled with gravitational information that could not be accessed through measurements of fields alone. The ripples of space-time created by merging black holes and colliding neutron stars carried messages from distant corners of the cosmos. To detect these ripples from space, scientists needed a level of measurement far beyond anything used to map Earth's gravitational field. They needed instruments that could track motion across millions of kilometers with accuracy finer than the width of an atom. Yet this remarkable sensitivity was not a leap into the unknown. It was the next step in a path paved by decades of precision gravitational measurement. Meanwhile, the study of gravity continued to guide spacecraft through the solar system, allowing humanity to explore distant worlds with confidence. Every time a probe passed a planet for a gravitational assist or entered orbit around a distant moon, scientists relied on models of gravity refined by countless measurements. The accuracy of these models determined whether a probe reached its target or drifted into the void. Each success reinforced the understanding that gravity was consistent, predictable, and aligned with the expectations of general relativity. By the end of this era, scientists had transformed gravity into one of the most precise tools available for studying Earth, the Moon, and the solar system as a whole. They had learned to listen to its faint signals, to separate its influence from other forces, and to interpret the changes it revealed. Gravity had become both a guide and a witness, recording the shifting mass of oceans, the flow of ice, the rotation of Earth, and the curvature of space-time. These measurements prepared humanity for the next revolution, when gravity would no longer be observed through static fields alone, but through waves traveling across the cosmos. The stage was set. The precision achieved by satellites and orbital experiments had reached the threshold where gravity could be listened to directly, not only measured. Soon, instruments on Earth would detect the faint tremor of space-time, and the next generation of space missions would follow, opening a new chapter where gravity itself would speak, telling stories carried across the universe. The refinement of gravitational measurement aboard satellites did more than reveal how Earth changed or how the Moon drifted. It prepared humanity for the possibility that gravity might carry information in ways that had never been measured before. For centuries, scientists treated gravity as a force that defined motion and shaped orbits. But the deeper they looked, the more they wondered whether gravity itself might be dynamic, able to shift and ripple as the universe evolved. General relativity predicted such behavior. It suggested that when massive objects collided or accelerated violently, they would disturb space-time in a way that produced waves, faint tremors traveling outward across the cosmos. These gravitational waves would stretch and compress the fabric of space as they passed, creating subtle distortions that could reveal the nature of their sources. Yet even as this idea gained acceptance, no instrument on Earth or in orbit possessed the sensitivity needed to detect such signals directly. The path toward listening to space-time began with the precision that satellites had achieved, because only through mastery of the smallest gravitational influences could the next leap be taken. Part of this preparation involved refining the understanding of drag-free motion, ensuring that satellites drifted along the true curves of space-time without interference. Engineers developed systems where tiny thrusters compensated for forces such as solar radiation pressure, maintaining the spacecraft in near-perfect free fall. The objective was simple but demanding. If the spacecraft drifted even slightly due to a force other than gravity, the signals scientists sought would be distorted or lost. Achieving near-perfect free-fall conditions required meticulously designed systems that could detect minuscule accelerations and respond immediately. This technology, tested and refined in Earth orbit, would later become essential for space-based gravitational wave observatories. At the same time, atomic clocks continued to play a central role in understanding gravity's influence on time. Each improvement in clock precision revealed new subtleties in the way gravity shaped the flow of time across different altitudes and gravitational potentials. These improvements, in turn, enhanced spacecraft navigation, deep space communication, and orbital predictions. But they also highlighted an important truth. Gravity's influence on time was not a theoretical abstraction. It was a measurable part of the universe's structure, and any experiment attempting to detect gravitational waves would need to account for it. Time itself would become one of the most important tools for listening to the faint whisper of distant cosmic events. Similarly, the study of Earth's rotation and interior dynamics revealed the extent to which gravity responded to even the slightest redistribution of mass. When Earth's crust shifted during earthquakes, satellites detected the gravitational changes almost immediately. When volcanic activity added mass to one region or removed it from another, the gravitational field recorded those changes. These observations demonstrated the instantaneous way gravity responded to mass. This responsiveness mirrored the theoretical behavior of gravitational waves, which would propagate changes in mass distribution across spacetime. The sensitivity required to detect such waves had been built slowly through these orbital experiments. Each mission sharpened humanity's ability to observe gravitational influence with clarity and confidence. Another essential preparation came from refining how scientists interpreted gravitational anomalies. The resolution of the Pioneer anomaly, once thought to be a possible sign of new physics, taught researchers the discipline needed to distinguish gravitational effects from spacecraft behavior. The lesson was clear. Before claiming a gravitational discovery, one had to understand the spacecraft in detail, from the heat it emitted to the sunlight it absorbed. This discipline prevented confusion and ensured that when gravitational waves were eventually detected, their interpretation would be grounded in rigorous analysis rather than speculation. Every anomaly required explanation, and only by eliminating non-gravitational influences could the true gravitational signal be isolated. These experiences helped create a culture of precision that extended across all space-based gravitational experiments. Scientists learned to combine multiple measurements using radio tracking, laser ranging, accelerometer data, and time dilation observations to create a unified picture. This multidisciplinary approach made space-based research more powerful than any single instrument. It meant that when gravitational signals arrived on Earth or were captured by future spacecraft, the scientific community would be ready to interpret them from multiple perspectives. Gravity could be measured as curvature, as motion, as time dilation, or as variations in mass distribution. Each method offered a different window into gravity's nature, and together they created a framework capable of handling even the faintest signals. As these capabilities matured, scientists began building and testing technology specifically intended for the next chapter of gravitational research. Among the most important developments was the LISA Pathfinder mission, an experiment designed to test the systems required for a future gravitational wave observatory in space. Although LISA Pathfinder flew years after many earlier gravitational missions, it represented the culmination of everything those experiments had taught. It used drag-free technology, high-precision laser interferometry, and exquisitely stable test masses to demonstrate that a spacecraft could achieve the quiet conditions needed for gravitational wave detection. Pathfinder proved that the required stability was possible, showing that the next generation of missions would be capable of listening to gravitational waves in the tranquil environment of deep space. The success of missions like LISA Pathfinder reflected a shift in how scientists thought about gravity. It was no longer viewed solely as a force shaping motion or a tool for mapping mass. It had become a carrier of information, a dynamic part of space-time capable of transmitting signals from regions that light alone could never reveal. Black hole collisions, neutron star mergers, and other cataclysmic events produced gravitational waves that rippled across the cosmos. These waves contained information about the mass, spin, and nature of the objects that created them. They carried the story of distant cosmic collisions across billions of years. To detect these waves, scientists needed the precision that decades of space-based gravitational experiments had nurtured. By the end of this era of refinement, gravity had transformed from a familiar presence into a scientific instrument of unprecedented power. Satellites had taught humanity how to measure it with sensitivity beyond what ground-based observatories could achieve. They had demonstrated how gravity responded to time, mass, motion, and geometry. They had prepared the foundation for a new kind of astronomy, one that would not rely on light, but on the movement of space-time itself. The world was on the edge of a new frontier. The next chapter would not begin with the launch of another satellite, but with the detection of a whisper from the universe, a whisper carried on waves of gravity, waiting for instruments sensitive enough to hear it. Gravitational waves were once imagined as delicate mathematical ripples in Einstein's equations, far too faint ever to be heard by instruments built by human hands. For a century, they remained silent predictions, hidden beneath the noise of Earth and the limits of technology. Yet the universe had always been filled with them, carrying the motion of black holes, the spiraling collapse of neutron stars, and the echoes of collisions too dense and violent for light to escape. When detectors finally reached the precision needed to sense these ripples, the universe revealed a voice that had been speaking since its earliest moments. The first detection arrived in the year 2015, a faint rising tremor created by two black holes merging more than 1 billion years ago. This tiny distortion, smaller than the width of an atom, stretched and compressed space-time as it washed across Earth. LIGO measured it with instruments that used laser beams bouncing between mirrors separated by kilometers, proving that space-time itself vibrated when massive bodies collided. Soon after, more signals arrived, each one a record of a cosmic event that no telescope had ever seen. Black holes of unexpected masses spiraled together, revealing populations unimagined in earlier models. Then came the neutron star merger, an event so extraordinary that it produced both gravitational waves and electromagnetic light. Telescopes observed the afterglow of the kilonova, while gravitational wave detectors recorded the spiraling collapse. Together, these signals showed that heavy elements such as gold and platinum were forged in the chaos of colliding neutron stars. The universe's chemical richness came not from ordinary stars, but from the most extreme environments ever observed. Ground-based detectors continued to expand this new sense, yet they remained limited by Earth's vibrations. Seismic activity, atmospheric noise, and the length of Earth-bound interferometer arms restricted their ability to hear lower frequency waves. These low tones, produced by supermassive black holes or ancient cosmic processes, could not reach detectors on the ground. To hear them, humanity had to take the instruments into space. The LISA Pathfinder mission demonstrated that spacecraft could maintain test masses in near-perfect free fall, shielded from disturbances so thoroughly that gravitational waves passing through would become measurable. Its success paved the path for LISA, a future observatory consisting of 3 spacecraft, separated by millions of kilometers, exchanging laser beams across the quiet vacuum. LISA would listen to the deep gravitational hum of the universe, detecting signals from black holes millions of times heavier than the Sun, and capturing the faint background left over from early cosmic epochs. Gravitational waves had transformed humanity's understanding of gravity, revealing it not only as curvature and attraction, but as a dynamic medium that carried messages, Across billions of years, the universe had begun to speak through space-time itself, and humanity had finally learned how to listen. Quantum mechanics and gravity operated for centuries in realms so different that unifying them seemed almost impossible. One described the motion of galaxies, stars, and planets, while the other explained the behavior of atoms and particles too small for the eye to see. On Earth, the two theories rarely met because gravity overwhelmed quantum systems, collapsing delicate states and preventing long-duration experiments. But in the weightless environment of space, quantum matter drifted freely, revealing how gravity acted on the smallest scales with clarity never achieved before. Aboard the International Space Station, the cold atom lab cooled atoms to temperatures so low that they formed Bose-Einstein condensates, states of matter where thousands of atoms behaved as a single quantum wave. On Earth, these condensates fell too quickly for extended study, but in orbit, they floated for long periods, allowing researchers to watch their wave functions expand and interfere. Atom interferometry in microgravity became one of the most precise tools for studying gravity at quantum scales. Clouds of ultra-cold atoms were split into separate wave packets that drifted along different paths before recombining. Any gravitational influence, no matter how faint, altered the interference pattern upon reunion. These experiments showed that quantum matter felt gravitational curvature directly, not merely through acceleration, but through phase shifts encoded in the structure of spacetime. Different atomic species fell with the same acceleration, confirming the equivalence principle at quantum scales with extraordinary precision. Sounding rocket missions such as the Maya series created Bose-Einstein condensates in space for the first time, proving that ultra-cold atom experiments did not need to remain confined to orbiting laboratories. These missions demonstrated that quantum systems behaved with unprecedented purity in microgravity, free from the vibrations and noise that dominated Earth-bound experiments. Future missions like STE-Quest and Beccal promised even more refined tests, including the comparison of different atomic species in freefall to search for subtle violations of equivalence and the study of coherence across extended distances. These experiments remained consistent with both quantum mechanics and general relativity, revealing no evidence of new physics, yet exposing the frontier where a deeper theory might one day emerge. Quantum systems drifting through curved spacetime brought scientists closer to understanding the boundary where gravity and quantum mechanics must eventually meet. Though the unification of these theories remained elusive, space provided the first laboratory capable of exploring their overlap with precision strong enough to reveal hints of future discoveries. As spacecraft accelerated across the solar system, relativity ceased to be an abstract concept and became a daily operational reality. Every satellite, every probe, every astronaut lived within a space-time shaped by velocity and gravity. Even the global navigation satellites circling Earth demonstrated relativity each moment. Their clocks ticked faster due to weaker gravity at orbital altitude, yet slower due to their high speed. If engineers did not apply relativistic corrections, navigation signals would drift by kilometers each day. Deep space probes revealed the same truth. Their radio signals shifted in frequency depending on their motion, creating relativistic Doppler effects that required careful adjustment. When spacecraft approached giant planets for gravitational assists, their speeds increased dramatically, and their trajectories curved in ways only general relativity could predict with precision. These missions tracked how time flowed differently across various gravitational potentials, proving again and again that Einstein's equations governed motion across vast distances. Even astronauts aboard the International Space Station aged slightly more slowly than people on Earth, their high orbital speed influencing their biological time by tiny but measurable amounts. Cosmic rays provided natural demonstrations of relativity as well. These particles traveled at velocities so close to that of light that their internal clocks slowed dramatically. Without time dilation, many would decay before reaching detectors aboard spacecraft, yet they arrived routinely, confirming relativity at energies no laboratory could replicate. Light passing near the Sun bent predictably as space-time curved, altering communication signals from distant probes. Spacecraft observed these shifts with extraordinary accuracy, reinforcing general relativity's predictions. Relativity became the foundation upon which all interplanetary navigation rested. It shaped every trajectory, every timing measurement, and every signal crossing the deep space network. Space travel revealed that relativity was not merely a theoretical framework. It was the geometry of motion, the structure of time, and the rule by which every fast-moving object experienced the universe. General relativity had passed every test within the solar system with remarkable precision, yet the universe presented puzzles that demanded deeper inquiry. Galaxies rotated too quickly for their visible matter. Clusters of galaxies bent light more strongly than expected. The universe expanded faster over time, driven by an unknown phenomenon called dark energy. These mysteries motivated alternative theories of gravity, but each one faced the unyielding requirement to match the vast archive of observational evidence. Modified Newtonian dynamics explained some galactic rotation curves, but failed in clusters and contradicted spacecraft data. Tensor vector scalar theories attempted to unify galactic and cosmological behavior, but struggled against constraints imposed by pulsar timing, gravitational lensing, and the cosmic microwave background. FR gravity offered adjustments to Einstein's equations, but faced severe limits from solar system tests and planetary observations. The Bullet cluster revealed a separation between visible matter and gravitational mass, supporting the existence of dark matter rather than modified gravity alone. Gravitational waves placed even tighter constraints. They arrived at Earth traveling exactly at the speed predicted by general relativity, carrying waveforms that showed no extra polarizations or deviations. Pulsar timing arrays further restricted how gravity could behave across large distances. All surviving theories had to reproduce general relativity's precision in the solar system and its predictions for gravitational waves, while still addressing cosmic-scale mysteries. This dual requirement eliminated broad classes of alternative theories, leaving only those that mimicked general relativity under most conditions. The evidence did not silence inquiry, it shaped it. Theories evolved, becoming more constrained, more subtle, and more consistent with observation. The universe itself acted as judge, allowing only those ideas grounded in measurable reality to continue. General relativity remained the standard not through tradition, but through survival, meeting every challenge while still leaving room for deeper understanding in domains where mysteries persisted. The future of gravity research stretched across the solar system and deep into the cosmos, carried by missions designed to observe spacetime with precision, far beyond current capabilities. LISA would become the first space-based gravitational wave observatory, listening to low-frequency waves produced by supermassive black holes spiraling together. Its 3 spacecraft would drift millions of kilometers apart, linked by laser beams capable of sensing distortions smaller than the width of an atom. These observations would reveal how galaxies formed, how black holes grew across cosmic time, and whether spacetime behaved exactly as general relativity predicted in its most extreme arenas. The Nancy Grace Roman Space Telescope would map the large-scale structure of the universe, studying dark energy through the patterns of gravitational lensing and the distribution of galaxies. The Moon would host laboratories where atomic clocks, seismometers, and quantum sensors operated with unprecedented stability, measuring time dilation and gravitational gradients in ways impossible on Earth. Mars would reveal its internal structure through combined seismic and gravitational mapping, deepening the understanding of terrestrial planet formation. Interplanetary atomic clock missions would test relativity more precisely than ever before, using time flow itself as a probe of gravitational potential. Long baseline interferometry using multiple spacecraft would allow the solar system to function as a single distributed observatory, tracking tiny motions of distant stars and detecting large-scale distortions in spacetime. These missions reflected a new truth. Gravity had become a language through which the universe communicated its history. As instruments grew more sensitive, this language revealed new details. Every gravitational wave carried a story of cosmic collision. Every shift in time marked the curvature of space-time. Every lensing arc traced the presence of matter unseen. Space travel had not rewritten gravity. It had illuminated it, revealing its depth, its precision, and its central role in shaping the cosmos. And as humanity journeyed deeper into the universe, gravity would remain the compass by which new discoveries were made.